The part that we need is totally generated. Okay, because what do we need? We need C of sigma 1 times C of sigma 2 times C of sigma 3. Let me call this way Z1, Z2, Z3, and times C tilde of Z1 bar. Let's call C bar of Z2 bar, C bar of Z3. We want to compute this expectation in the BC system. Now, in our general discussion on scattering amplitude, we had this lovely little discussion on how this was essentially a determinant. Okay? What determinant was it? Well, if you've got analytic and anti-analytic terms, it's the product of two determinants. And what were the determinants? The determinants were the value of the three zero modes of this. You take three zero mode functions of the C fields, of the P operator acting on C fields, evaluated at these three different points, Z1, Z2, Z3. That gives you a 3 cross 3 matrix whose determinant you take. But what are the values of these? If we're working with the plane, what are the values of these zero mode functions? Somebody? What are the functions? The zero modes of the operator P. Formerly they were all analytic functions because P operator on this plane which is del bar. Very good. But we computed that only 3 of them were globally well defined. What were these 3?
1, 2, Z and Z square.
Perfect. The 3 things that were well defined were constants Z and Z square. Okay? So what we want is constant evaluated at Z1, Z2, Z3. Z evaluated at Z1, Z2, Z3. Z square evaluated at Z1, Z2, Z3. Times the complex conjugate. Okay? Now what is this determinant? Well, you can calculate it, but we can be even slicker. It must vanish when any of Z1 and Z2 are equal. And it must be of degree, let's say, it must be of degree 3. What are the options? It has to be Z1 2 times Z1 3 times Z2 3. It has to be proportional. Times the number, we don't care about numbers. Okay, so this determinant is Z1 2, Z1 3, Z2 3, and then times complex. You get complex conjugate determinant, so you have mod square. Okay. So if you are willing to use our determinant way of doing the computation, we're through. At least for this one. It's very simple guy. 3 insertions. But if you have a completeness, then we also give you the conformity theory of differentiation. More or less trivial, right? See, suppose we were computing this object, CZ1, CZ2, CZ3. Then, what are the singularities in the OP? CZ1, CZ2, CZ3. Somebody? There are
only singularities in the BC.
Exactly. So there are no singularities in the CZ1, CZ2, CZ3. Okay? So this answer can have no singularity. Moreover, it must have a 0 when Z1 is equal to Z2. Why? Because these are anti-commuting fields. CZ1 squared is equal to 0. Okay? So it must have a 0 when Z1 is equal to Z2. So it must be of the form Z1 2, Z1 3, Z2 3 times some function that's analytic in the Z's. Analytic in the Z's, and we're not going to say anything else. Okay? Alright. Now, C is an object of weight minus 1. We did a lot of calculations with del x, which is an object of weight 1. And we found that in order to be well defined in the U plane, it had to grow like 1 over z squared. It had to go like 1 over z squared. If we do the same thing with its object of weight minus 1, Now 1 over z squared will get flipped. Okay? So C, we did this calculation last lecture. C can grow at, is allowed to grow up to z squared. It's allowed to grow at infinity like 1 z or z squared. That was the origin of these three modes. These three zero modes that went like 1 z or z squared. Okay? So C can grow like 1 z or z squared infinity. But now you look at this answer. And this thing already has 2 powers of z1. Already has 2 powers of z2. Already has 2 powers of z3. So in each of the three variables at infinity it already grows like z squared. Therefore the remaining function can at best grow as fast as a constant. It must be analytic, therefore it must be constant. Okay? Therefore this correlation function has to be z1, 2, z1, 3, z2. No other options. Alright. Now I'm going to leave the following as an exercise to you. Suppose we had the insertion of m c's and m minus 3 b's. Okay? Use the same argument to determine the correlation. Okay, maybe it's too difficult. Let me give you the argument. And then we solve this. Okay. Suppose you had m c's. So c of zi, I is equal to 1 to n. Let's call it n plus 3. And we have b of z tilde j, j is equal to 1 to n. Okay? So what we can do is to write a function that has all the right singularities and zeros. Okay? And then multiply it by some analytic function and see what we can, how that analytic function is constrained. So a function that has all the right zeros is something that has a product of zij for every c and a product of z tilde ij for every b. A function that has all the right poles is a product that has zi minus z tilde j, the denominator, for every pair of I and j. Okay? So now let's see how this function grows at infinity. So we're going to write that down. I said in words, but we're going to write that down times an analytic function. Okay? Now let's see how that function grows at infinity in the z, let's say z1 variable. So in z1 variable, we had product with m minus 2 other c's. But in the denominator, we had a product with m other b's. Sorry, m plus 2 other c's and m other b's. So at infinity, it behaves like z squared. So the argument that we given was to this thing. It tells you that this function has to be constant as far as z1 is concerned. That was of course for all of the z's that appear in C. Now let's look at the b's. In the new, remember firstly that b had weight plus 2. Okay? It must vanish twice as fast as something that has weight plus 1. So it must vanish like 1 over z to the 4 at infinity. Okay? So this we also derived last class. Okay, so now let's do the calculation of the b's. The b's with other b's, there are m minus 1. Okay? The b's with c's, there are n plus 3 such things. So it behaves like 1 over z to the 4. Therefore, the remaining function must be constant in the arguments of the b's as well. So therefore, the remaining function must be constant. Therefore, the answer to this correlation function with arbitrary number of c's, obey the Riemann block theorem, of course. So, m plus 3 c's and m b's, we just determined it up to no problems. It's the product of all z's pairwise in the c's, product of all z's pairwise in the c's and b's, divided by the product of all z differences between b's and c's. That's the answer. Upper constant.